So we will resume from what we have been doing. You recall we have been trying to reduce the uh, 4-degree vertex cover problem to exact cover. Our aim is to claim that exact cover is NP hard first. Then we will prove it to be NP to show that it is NP complete. So how do we go about the reduction is what we are going to see. We had looked at the exact cover problem, what it was. I'm just quickly reviewing it. We are given a pair SU where S is a finite set of elements and U is a subset of elements of S. So we want to find out whether there is a subset of U which contains within its sets every element of S once and only once, which means does U contain within it a partition of S. For example, if the set of elements is ABC and U is ABBCCA, then it does not belong to vertex cover, as we had seen in the previous class. If the set of subsets is ABBCCA, then it can, that is ABC. Hence, the whole thing belongs to exact cover. That's what we had said in the last class. You recall we had also said this. A reduction means that we have to convert GK when GK is an instance of vertex cover uh, to SU, where SU is an instance of exact cover. So that GK belonging to 4-degree vertex cover would be logically equivalent to SU belonging to exact cover. And also this transformation has to be done in polynomial time. That is order of the size of the graph, number of steps. So we had started with the construction. We had said that we proceed as follows. We take the set of elements S. We have to construct that is a set of elements S, and we have to construct a set of subsets. Then we had said that we would be taking two input instances just to demonstrate as we go. So the first was a graph G in which there are three vertices ABC and three edges E1, E2, and E3 named as given, and K is equal to A. As we know, this is an instance where it belongs to vertex cover because there is a vertex cover size 2. And the second input instance was the same graph but with A equal to 1. And so we know there is no vertex cover of size 1, so it does not belong to vertex cover, 3D, 4D vertex cover either. So these have to get mapped in instances to the exact cover problem, which belong and not belong respectively. So we had started looking at the construction steps. We had said that we would be constructing the elements in the. He said for every vertex label, we add an element. So the set of elements will contain ABC in this case. So wherever it is, all the vertex labels will be added into uh, the set S. Then every edge label becomes an element. So we have S, A, B, C, E1, E2, E3. Then we said that corresponding to K, we would be adding some elements x1, x2 up to xk, which are symbols which are like named x1, x2, xk, etc. One to represent each possibility or possible xk. So, possible instance. So in that way, what we add is one unique label, which is going to help us with the logical equivalence mapping. So one element for each. So in the first case, we would be adding x1, x2. So you would get S equal to ABC, even E2, E3, x1, x2. The second case, S equal to ABC, even E2, E3, x1. This is our revision. Then we were talking about how to construct edges. So I'll get back to it. Not how to use the edges in order to construct our uh, U elements. So the sets in U is what we want to construct. So let us do this. So we said that the sets in U would proceed as follows. Corresponding to every vertex label, we would have a subset V. Okay. So in this case, we would be having sets like A, B, and C. Okay. So with vertex labels, we have elements. Secondly, what we do is for each vertex, we take the adjacency list, we would say, of edges by edge labels. So for A, we would take, in this case, I think it was E1, E2. For B, in this case, it must have been, I suppose, I'll just look up. For B, it was E1, E3. For C, it must have been E2, E3. So these are all added. I mean, these all need to be added, but not exactly in this way. Let us. What we are going to construct is we will also be adding all the subsets of these sets. Okay. So, which means that we'll have something like E1, E2, E3, not E3 over here. We have 5, right? Also, we'll also be having E1, E3, 5. We'll be having E2, E3, 5. 5 minutes. It's 5. Then we add just a second. Then we add a vertex label to each of these 6. Okay, so that in this case we would be getting E1, E2, A, E1A, E2A, and A. Here we would be getting E1, E3A, E1, sorry, B, E1B, E3B, and B. And here we would be getting E2, E3C, E2C, E3C, and C. That being done, now we will augment these sets further. Augment further. What we do is we add each X label to each of these sets and add all those sets to you. So what happens when we add that? Let us just see. I'll just use a different color just to illustrate. So what we're going to do is, to this we are going to add x1, 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 x1. We are going to add x1, x1, x1. To this also we are going to add x1, 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 x1. Okay. So This forms a part of U for the case 1, and this forms the whole of U along with this part for the second example, in which K was 1. If K was 1, only X1 is possible. So that is it. So it means that we will do that in the next week. Before coming to that, so this and this together for case 2, that forms the whole thing, right? Now, as far as case 1 is concerned, we had two x values. So this would be added. Plus, in addition, we would be taking the union of this replaced with x1 replaced with x2. Okay. So with x2 replacing x1, we will have another set x2, that is x2, 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 x2. We would be having another set of items that is going to be added to uh, uh, the set that we have constructed. Okay. So if you want, I'll just illustrate by writing out the whole thing so that it will be clear to you what exactly is our S and what exactly is our U. So what we have constructed, case 1 and case 2 is, case 2 being smaller, case 1 is this A, B, C, E1, E2, E3, X1, X2, right? And case 2, it is A, B, C, E1, E2, E3, X1. Now what is U? U in case 1, that is when x equal to 2, it is going to be, as we have seen, it's going to be a big set containing A, B, C. In addition, it is going to contain E1, X1, E1, X2, right? E2, X1, E2, X2, then E3, X1, E3, X2. No, just a minute. Just let me go back up. Apart from this, we will also add the vertex label over there, as we had said earlier. What we would have here is this A as well. So I have to add that, right? So let me come down and again finish that by adding excess A and others as well. So E1, X1, this is coming from A. So we have put A over here. A will also be here. Then E2 again from A, the vertex A, E2 again from the vertex A. Okay. Now we had gotten E1, E3, right? So E1, X1, B, E1, B, E3, B, X1, right? E1, X2, B, E1, E3, X2, B would be there because of B. Now we would have E2, E3 for C, right? So E2, C, X1, E3, C, X1, E 2cx2, 3cx. Then there are bigger ones and also things containing just the vertex. So let us get on to 3. So we would be having E1, E2, A, X1, E1, E2, A, X2. We would be having E1, E3, B, X1, E1, B3, B, X2. We'll have E2, E3, CX1, E2, E3, CX2, right? So these are our two element sets. Apart from that, we had seen that there was a 5. Now when to that 5 A and X1 are added, we will get that version as well. So we will have AX1, AX2, we'll have BX1, BX2, we'll have CX1, CX2. Okay. What about case 2? Case 2, we will be having most of these. In the sense, we would be having only the X1 version. So we'll be having A, B, C as different sets. Then we would be having E1, X1, A. We won't have X2. Then we would be having E2, X1, A. We won't have X2. Then we would have E1, X1, B. E3, X1, B. E2, C1, X1. E3, C, X1. Then we will have E1, E2, AX1. Then we would have AX1. We would have E1, E3, BX1. We would have BX1. We would have E2, E3, CX1. We would have CX1. This would close. So these would be the U in case 2. This would be the case 1. That's something we can see. Okay. So that's our construction. Now construction is polynomial type. Why? Because how many vertices have we added? We have added vertices equal to number of vertex labels plus number of edges plus k. So that is k number of vertices. So it has to be less than equal to number of vertices. So because the max vertex cover size is the set itself. So vertex labels so this is going to be the order of n square where it's in this analysis. That is about the set S. How about U? Now U is going to have, as we said, for each degree of a vertex, we will have one element in the big set. In the biggest set. And then we have all its subsets. If this was not degree constrained, it would have gone exponential. But we have said that degree is constrained by 4. So that's where the importance of the degree constraint comes. So because the degree is constrained, this set can be at the most of size 4 in any graph. In our case, it was 2, but here it is going to be constrained to 4. So when we take all its subsets, we can have at the most 2 raised to 4 equal to 16 subsets. Okay, which is a constant. So in the 16 subsets, what we are going to add is for 16 subsets for n vertices, we will have n into 16 subsets. Each of them we are going to repeat with one value of x. So we are going to have 16 nk number of them, which again is order of n square. So hence construction is so then what is left? We have seen polynomial time. Now what is left to prove is that what is left to prove is that uh, GK belongs to 4D vertex cover. It's logically equivalent to the SU that we just constructed belongs to exact cover, which means that U contains within it. Now we can note that if GK if GK belongs to 4D vertex cover, 4D vertex cover, then the what we have constructed like this SU, it belongs to it. How? Now let our graph have a click of let G have click of size K. Let it be V1, V2 up to Vk. Then we can show the exact cover as follows. We do is we choose x1. We choose the set that has x1, v1, and all edges adjacent to v1. Okay. Then we remove that edge from the set of edges. So let's start with our t equal to set of edges. Okay. Then we remove them from t. Then we take our next vertex v2 and we take x2 v2, one with all adjacent edges present in T. So if something was already adjacent to come over here is the idea. We do have a set like this because we have all the subsets around. Then we remove them also from T. And in this process, at some point of time, if we run out of edges, what we can do is then we would be taking For example, say at V something. V, what do we call it? We run out of edges. Okay, because our set becomes empty or does not have any edge that is adjacent to this particular VI. Then what do we do? Then we just take that without edges. We would be just taking Xi, Vi set and putting it inside. Okay, so this we continue up to Vk, Xk, and all adjacent edges, if any, present in T. Present in T. Now our claim is that all the edges get covered in this. Why? Because vertex covers all the edges. So all the E1s, E1 to last E last get covered in one of these sets. Right? Also, all the vertices V1, vertex labels V1 to Vk. Plus all vertex labels V1 to C plus all the extra variables x1 to xk get covered. Now what remains is edges in G that are not in vertex cover. Okay. So how do we account for these vertices? So what we do is we already have their versions V label of not covered vertex. So those also we add to here so that we get a cover. So we get exact. I can illustrate this process with the example next. So for example, in our case, when we take x1, let our vertex cover be what were the A and E? Okay. So we take x1, we take with it along with A and the adjacent edges E1 and E. Okay. Then starting with our T equal to E1, E2, E3, what would have happened would be E1, E2 got deleted, so T becomes T equal to E3 after this point. So we take the vertex B along with x2 and we take the remaining edge which is adjacent to B, that is E3. And we take the next set. You may note that all these sets were present, right? Now, we have x1, x2 covered, A and B covered, E1, E2, E3 covered. And T is over. But we still have a vertex C that is not covered. That is a part of our S. You may be remembering our S. It had all vertices, vertex labels, it had all the edge labels, and it had x1 to x2. So we take just the element C which we had added first. So our U equal to this is the exact cover which is present. And it is present because that receiver set. Now, in the second case, you'll note that if case 2, okay, we had only one x. So with that x, we may have put, so suppose with one x, we would have put one symbol that is x1, e1, e2. Now what remains is b and c, and what remains is t with e3 in it. But no, we don't have anything left to, cover it. So that's why it does not come out is what we can see. We'll prove the reverse way also because that needs to be done. But before going to that, let us just, I hope you appreciate that if we have a vertex cover, all the edges get covered, right? And we have a way to form the exact cover. If there is no vertex cover of that size, then all the edges will not get covered in this process. What remains is the edge that is not covered. Now, this proves only in the forward direction. You next have to prove that exact cover implies that there vertex cover of size 4. Not for size 4. Vertex cover of size K. Now, in this exact cover, we must be having all the elements from x1 to uh, all the elements x1, x2 up to xk, some special variables, right? Special introduced variables covered. Covered because it's an exact cover. Now, these can't all belong to the same set or pairwise. Each of them should belong to a different set. Okay. So when each of them belongs to a different set, because it is each of them, as we know, comes only in conjunction with the vertex. Right. Now, when it comes in a conjunction with the vertex can't be repeated because vertex label can't be repeated because it's an exact curve. So each of them, there must be a unique vertex. So there are k of them. And we claim that these form a vertex cover. Vertex cover of size k. Now, why should that happen? Now, we can note that because it's an exact cover, all edge labels are covered. If an edge label is covered, it can be only with the adjacent vertex, isn't it? So in each set represents the vertex that covers the edges in the set. It has to do it because that is how the sets were made. It is not possible that a vertex and X label come, but then there is no adjacent edge. Because that edge must be there with something else, which is another adjacent vertex with another label. Otherwise, it has to be there. So in this way, that it is ensured that all the edges get covered. So in addition, so what that means is this set of K represents a vertex cover. And if we count the number of isolated vertices, which means vertex labels with just come as themselves, that counts for V minus VC. Okay. So the K in question is the number of X variables, which is the same as V minus VC. If we just count the number of vertices that come in the exact cover without any other element in the X. So that completes the proof. So which means that uh, exact cover is in Bihar. Now it is easy to prove that exact cover is NP. Reason being that we just have to give a polynomial time algorithm. So verification algorithm would have S, U, and a sample covering set. So we just have to check whether every element in S occurs in a set of C and only in one set of C. And also if C is a subset of U. So if both these are true, our case is done. We have to return a yes, otherwise a no, which would mean that C is not a certificate to SU belonging to S. So but if C is a certificate, it will satisfy these two characteristics and hence it's removable. This can be done in polynomial time using a suitable set representation like a matrix or expression, which is something you can verify. So I'll conclude with this. Thank you.